Okay, today we're going to be talking about the force-velocity relationship of human muscle. Let me get my laser pointer on the screen here. So the way we measure our force-velocity relationship is using a machine called an isokinetic dynamometer. Essentially what that means is it's got a load cell embedded in this arm here, this rotational area, and then it has all these multiple attachments. So today we're going to be doing knee extension and flexion on our participant Ian here, and I'll be operating the computer. So embedded, like I said, it has a force sensing element, so the amount of force that Ian is putting out is going to be measured, but it also has a robotic component. So what that allows it to do is not only move at a given speed and apply a set amount of resistance, but also push back. So our force-velocity relationship, a little bit of what we want to think about how as we get into eccentric forces, we have an increase in force is due to this passive force here. So as we stretch our tissues, we have an increasing elastic component, and as you stretch not only the muscle fibers themselves, the connective tissue embedded within them in their cell membranes, but also the connective tissue around it, the collagen fibers and connective tissue in the tendons, you have this increase in passive force. So just like an elastic, the longer you stretch all those tissues, the more force that they're storing up, the more potential energy, and they can then release that back into the system. So then when you combine that with a maximal effort, such as the active force, you can actually get really high increases in additive or summative forces when you add even small active forces to really high passive forces. So that's going to be contributing partially to our force-velocity relationship. The other part on the shortening side is that the coupling of the myosin heads on the actin filament, as they bind, they just simply cannot grab, interlock, and then turn quite fast enough to keep up in those concentric speeds. So you've probably seen a graph like this. On the left, we have the eccentric, so a negative velocity of shortening of the muscle. So even though the muscle is contracting, it's lengthening. And then on the right side, you have the velocity of shortening getting positive, so meaning that as the muscle is actively contracting, it's also shortening. So in our black line here, we have an isolated muscle prep. So the maximum eccentric strength is, like I said, that maximum summative potential between the passive elements and the only little bit remaining active element as it gets stretched as fast as possible when you have very little cross-bridge binding. And then as you can see, as we get to zero velocity of shortening would be an isometric contraction, or a contraction where there is no movement. And then what you can see is that that dips down, and as we increase the velocity of shortening, you decrease the ability to produce force in those increasing concentric speeds. And the reason for that is that there is simply not enough time to mechanically bind the myosin heads to the actin filament, go through the power stroke cycle, and pull on that. Think of your car when you put the pedal to the floor. It's a summation of a million little explosions, and to transfer mechanical power from the engine to the drivetrain to the wheels to the road through the rubber actually takes a little bit of time. Very, very short instances of time, but it does take some time. So on the concentric side, that's what you can kind of think of. The faster that muscle has to be moving, and those myosin heads binding, releasing, and then moving along, there's just not enough time for tension to build up through the entire mechanical system. And then you can see this dotted line here in vivo. In vivo, you're not going to get quite as drastic effects in vivo, meaning in a person versus an isolated muscle prep. On the eccentric side, this is probably a little underestimating it. You can probably get a little bit more eccentric force than you could isometric, but it is marginal, and that's because there's what's called a neural tension limiting factor, or a neural protective mechanism that will simply not allow these muscles to be massively overloaded above what a typical isometric maximal force output would be. So if you're recruiting 100% of your motor units, you're recruiting the muscle absolutely maximally. you have organs in your muscle spindles and Golgi tendon organs in the tendon, which will then feed back into inhibitory mechanisms in the spinal cord, and then limit the amount of actual recruitment of those motor units. So your recruitment will decrease and that tension will fall off and not get as high as it possibly could in an isolated prep. So here I'm going to again pull back to Ian, and the analogy I like to make here is just to remind everybody that he's going to be contracting his quads on the way out, and then he's going to be contracting his quads as he's like kicking out typically, but this time what the robotic element is going to do is it's going to be pushing him back. So if we zoom in here, we'll sort of like do a little analogy on that. So let's start off with concentric. Concentric is like if you're winning an arm wrestle battle. You're still trying really hard, you're still pushing down, and somebody is resisting you, but you're actually going through muscle shortening and recruiting those motor units, and that muscle fiber is then shortening, but it's still doing very, very hard work. So in terms of the analogy I want to give, I want to start off here with Ian's leg, and starting off in a fully sort of flex 90 degrees position. And we'll use these force vectors to give us the analogy. So him being concentric, if he's kicking out this way, he has a larger force vector from his leg than the machine is exerting. Now, it's going to limit him at given speeds, and it's going to exert as much force as it needs to, but it's always going to be a little bit less than what his leg is exerting because he's moving the robotic arm or the robotic element of it forward. So the force vector from his leg is going to be a little bit larger than from the dynamometer, and as he kicks out, that muscle, whoa, my cursor's going crazy there, that muscle is shortening. That's what a concentric contraction would look like. Okay, sorry, I lost my place in the slides there. I had to take a little bit of a break, but if you're going through an eccentric contraction, you can think of it like you're facing a stronger arm wrestler than you. So you're exerting absolutely maximally, that muscle is contracting maximally, but it's not able to shorten or even stay isometric. It's losing that arm wrestle and is lengthening throughout the entire process. So that's the eccentric contraction taking place. So if we go back to our analogy here, we can see that his leg is going to start out and the robotic element is going to be pushing down with as much force as it needs to override his force output and move at a given velocity that we've programmed into the system. So we have a much larger force vector from the dynamometer than from Ian's leg, and as he keeps kicking out, he's still kicking out. Think about that losing battle to the arm wrestler. His muscle is lengthening. So as he's kicking out, his arm or his leg is being pushed back, and that muscle is lengthening. So what we're going to do here is I'm going to walk through what the video was, and I'm just going to duck off here and show the video in full screen, but I'll continue talking through it. Okay, so first we're going to start off with our concentric contractions, remembering that Ian is kicking out against the force dynamometer, and then what we're actually going to do is measure both his quadriceps and hamstrings. So making sure that, can you see my cursor there? Yep. Okay, so making sure that as he's kicking out, as his leg is moving out, he's contracting his quads, they're shortening, and then as the arm is all the way up, he's pulling back with his hamstrings, so they are shortening. So we're going to get measurements from both. What I'm doing here is I'm just setting him up, making sure that the range of motion is applicable, and we're going to go through the full range of motion. The first speed is going to be the slowest speed, 30 degrees per second, and like everything sort of experimentally, we have to show that we're going to measure it at multiple points to then prove that, okay, we actually have that relationship like we're seeing. So we're going to measure 3 speeds concentrically and 3 speeds eccentrically, deviating from that zero velocity, which would be isometric. Here's his 30 degrees per second. So he's pulling back with his flexors here, and then he was extending with his extensors. So we got 3 reps in there, absolutely maximally. Then we're going to move up a speed to 90 degrees per second. And so he's going to pull back to start it. kicking out with his quads, pulling back with his hamstrings, out with his quads, back with his hamstrings, but the machine is exerting slightly less force, allowing him to move faster. And like I said, that mechanical tension that's building up in the system is just going to be less because you can't have the proper mechanical coupling and the transmission of force through the entire system. Finally, we're going to do one last speed here, 150 degrees per second. This is pretty fast, but feels fairly natural when you're doing something concentric. You're pretty comfortable with doing that. Your muscles are used to shortening. Eccentric is where you really have to coach somebody through the system and explain what it's going to feel like, and then they have to resist it going the opposite way. So they think that they're going to pull back with their flexors, but really they should be kicking out with their extensors, so the machine forces them back. Again, I'm just setting the range of motion here, making sure that everything is in accordance, setting the stops. And then you'll notice that Ian is pretty good at this. He's pretty practiced. So he knows to continue kicking out, and there's very little sort of jitter in the system. But even then, you have to be super, super practiced to get the full effect. So he's kicking out here, he's kicking out here. Even though it's going back, he's kicking out with his quads, and then now he's pulling with his hamstrings as it goes the other way. And now he's going to switch, kick out with his quads, kick, 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 and then pull with his hamstrings, pull, 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 pull. And you can see that he's losing that battle because this can exert up to 600 Newton meters of force. So really it's going to overwhelm any person's single leg. We're going to again do the same thing, moving that speed increasingly negative on that graph, if we're referring to that graph. So here was his 90 degrees per second. He's pulling back hamstrings, kicking out quads. It's just a little faster. And then he's got his rest in between, and I've obviously skipped all those. And then we're going to move to our 150 degrees per second eccentric, and this is pretty fast. Anything at these speeds, you really have to have a participant or patient that's very comfortable working at these speeds for them to even get any activation and not just completely back off. There you go. All right. So Ian's done there. That was our testing session for our eccentric strength at 3 different speeds, 30, 90, and 150 degrees per second concentric and eccentrically. So, let's start. My pointer back here, and if I switch my screen share, boom, okay, there, I'm back. So what we're going to do now is look at the data, and this is how the data outputs. You can see that in the video he was doing his left leg, so we actually have no data for right leg. I didn't actually test his right leg at any point during that test, and you can see that it says deficit here. Pre-programmed into this system is if somebody had an injury, you can say their affected side versus non-affected side. We're just going to ignore that because obviously there will be no deficit. We didn't test right or left leg, and Ian's not injured. So what we're going to do is look at his peak torque from his best repetition, and we're going to pull that out. So that you can see that we have his extensors or quads here and his flexors here. Both of these are indicating that the test was concentric. Concentric both ways, and it's indicating our speed here being 30 degrees per second, so our slowest speed. And you'll notice this in your data collection sheet that the first box you're going to write in for extensors, 30 degrees per second concentric is 168 Newton meters, and then for flexors it's going to be 98 Newton meters. We're going to work through that, and I'm going to write that into my table here, 168 and 98 Newton meters. We'll move on. Again, looking at the next speed, so 90 degrees per second, extensors or quads, 137, and then 84 for our flexors. So then if we're comparing that, we see a decrease in both our extensors and flexors, and we said moving concentrically, that's what we'd expect. So the trend is going in the right direction. And then 123 and 75 at our 150 degrees per second here for our extensors and flexors. So we'll write that into our table, and what we can see is that we have a pretty nice trend of decreasing peak torques for both our extensors and our flexors. So both of them are following that graph that we'll take a look at the end in terms of decreasing ability to produce force as velocity increases concentrically. Okay, so now let's take a look at the eccentric data. Eccentric on our extensors and then eccentric on our flexors. At 30 degrees per second here, slowest speed. Again, we're going to look at just our peak torque for that best repetition. We have 183 for our quads and 103 for our hamstrings. I'll write that in the table. Then we'll pull this one up. So we actually had a decrease, which isn't necessarily expected at our 90 degrees per second. And pretty much the same for our flexors. If we write that into our table, we've got 157 and 108. Again, we expected something to stay steady or even slightly increase here. So this might just be a factor of the increasing speed. The patient isn't always super comfortable. And again, this is a one-person mini experiment or demonstration. So what we can't necessarily expect the averages to work out here. That's why obviously you would collect multiple participants, and in all the research that proves this, they had very practiced participants which did this test multiple times and had familiarization trials before they collected their data. But we'll check our next data. Whoa, if I just skip it like that, we'll check our 150 degrees per second here, our extensors, so our quads, back up to 186, and our flexors a little higher at 111. So if we write that in, we can see that our flexors had a very slight trend to increasing for our eccentric speeds as we increased eccentric contraction velocity. And then we had a little bit of a hiccup here, dropping about 26-ish Newton meters down in our knee extensors, but then it popped right back up. So he might have just not necessarily been giving it his all as he detected that speed increase on that rep there, but you can never necessarily know. But we've got a pretty good trend in both directions. We saw it stay fairly steady with the little blip in our extensors, and our flexors stayed steady or even increased a little bit eccentrically, and then concentrically we saw them both drop off, decreasing as velocity of shortening increased. So that's a quick little demonstration of force-velocity relationship. Thanks for watching.